Swayam Prabha. Digital India. Educated India.
So, what I thought I'll do is just give some concluding remarks of the problem that we saw yesterday, where we looked at the flow through a pipe network which had one branch. Okay. So, one thing we saw is the equations for the branched pipe came from the conservation of mass and momentum. Okay. And the assumption we had made was that the flow was laminar, and because of that assumption the equations were linear. Okay. So, just to emphasize, so the assumption of laminar flow ensures linearity. So, for example, if the flow had been turbulent, the relationship between the pressure drop and the velocity won't be linear. So, what do I mean by linear? By linear, I mean if I were to double the pressure drop, my velocity would be doubled. That is what I mean by linear. Okay. Non-linear means if it is doubled, velocity will have some other scale. So, that is the only thing. And finally, we can write those equations in the form AU equals B, because of the assumptions we made. Because we had linear equations, we could write it in the form of AU equals B. U is a vector which contains these velocities V1, V2 and V. B had the is again some vector which had delta p 0, and A is a matrix which had elements which depend upon L, L1, L2, D1, D2, etc. Basically, the elements that you had were dependent upon these variables. Okay. So, now when it comes to solving a problem, you know what these variables are. With the viscosity L1, L2, you will put those numbers, put those values, get the elements of the matrix A, you know the pressure drop which you are imposing, you will get the matrix B, and then the unknowns are this. Okay. So, basically when you were doing your math course, you had an equation of the form Ax equals B. You were just solving it as a mathematical problem. You did not really think of this as having any physical significance. All I am trying to tell you is that there are contexts in engineering where these kinds of equations arise. Okay. And there is a physical significance to the variables that you have, and when you get the results, you have to analyze the results to make sure that some sense comes out of it, that they are sensible. So, the other thing which we assumed was that the system was at steady state. Okay. So, those are some of the assumptions we made, and with this an example of a problem in fluid mechanics where you get a system of linear algebraic equations. So, if you have linear algebraic equations, I can write it in the form of AU equals B. Okay. U is what I have to find out, B and A are given to me. I want to go to another example where we are not talking about steady state, but we are talking about an unsteady state situation. Okay, unsteady state situation means the things are changing with time. Okay, so the first thing which comes to mind is a batch reactor. So if you have a batch reactor, you have a situation where as the reaction progresses, the concentrations of the species are going to change with time. If it is a reactant, it will decrease with time. If it is a product, it will increase with time. Okay, and it could be reactant and product. Sometimes we have to solve the problem to figure out if it's increasing or decreasing. So basically, the next example is of a dynamic system where we are doing a simulation where variables change with time. An example is batch reactor. Okay. So, I am going to consider the following set of reactions: A giving B, giving C, and A giving D. So, this is K1, this is K2, and this is K3. So, these are rate constants, okay, and I am going to assume my reactions are all elementary. So, that means that all my reactions are first order. Okay. So, reactions are the order of each reaction is 1. Okay. So, now, so that is the difference between the earlier problem and this problem. Earlier problem at steady state, so no time dependency, but here there is time dependency. So, again you have to write your mass balance equation for all the different species and then get your governing equation which describes how the concentrations change with respect to time. Okay. So, again conservation of species has to be written, and if you realize this, you have this term accumulation equals in minus out plus generation, and for the batch reactor nothing is coming in, nothing is going out, so in and out are 0, okay, and that goes off, and then you have only these two terms remaining, and if you write it out you would get something like dCA by dt is not getting generated, it is getting consumed, so you will get minus K1 CA minus K2 CA. A is getting consumed by these two reactions. dCB by dt, as far as B is concerned, it is getting produced by A, it is getting consumed by this. So, I will have K1 CA minus K3 CB, okay, and as far as C is concerned, I have that is equal to K3 CB, okay, and as far as D is concerned, so Basically what I have done is written the governing equations for each of the species, and that is just what you are comfortable with. The first thing is, again I have made an assumption of the thing being elementary or first order. That is an assumption, and because of that assumption all these are occurring to the first power, and because what are the dependent variables here? The dependent variables here are the concentrations A, B, C, D, and I also have time derivatives, first order in time. So basically I say that this is a linear system because the power for all this is 1 and the derivatives are also occurring to the power 1, okay. First order derivative to the power 1, second order derivative to the power 1. So this is basically again a system of linear equations. If I had CACB or CA squared, then it is not linear. If I have dCA by dt whole square, it is not linear, okay. So now because it is linear, I can again write this. So now the unknowns in this problem are, the unknowns are a function of time, okay. And so basically I am not going to write it for everything, Ca of t etc. I am going to recast this system of equations in again this vectorial form that we spoke about earlier. Now remember all of these are functions of time, okay. I am just rewriting it in a vectorial form. I am going to write this as some matrix so again this is a vector, this is a function of time, this is also a function of time, and I have to get this matrix here. So the first one has only d dt of Ca has minus k1 minus k2 0 0 0, okay. So this is going to be a 4 by 4 matrix, we have 4 variables now. What about d dt of Cb? k1 multiplied Ca minus k3 multiplied Cb. So I have k1, I have minus k3 and 0 0, and this is Cb, this is k2, I think what is this? This has to be k1, no? Yeah. So basically if you were to do this matrix multiplication and expand it out, you would get this. So I have just represented this system of equations. So earlier also had a system of equations, I put it in vectorial form. I am writing again a system of equations in vectorial form, and this I can write as d dt of u equals matrix A times u, okay. So u is this thing here, A is this matrix here. So what we have now is a system of ordinary differential equations, okay, and by writing it in this form I am trying to get to the point where I say, look, this that perspective, that universal framework that I spoke about is going to come out, okay. That is the reason we are doing all this. So now in order to solve the system of equations you need to have an initial condition, so which I have to specify at t equal to 0 u equals some u naught. So now this is the initial condition at t equal to 0 u equals u naught. Okay. Basically, at the beginning of the experiment, when you are loading your reactor, you possibly loaded with A, okay, and so you will have, what is U naught? U naught is a vector again, which contains, which has 4 things: CA naught, CB naught, CC naught, CD naught transpose. Okay, I am not writing it as a column, I am writing it as a row. So at the beginning of your reaction, what is the concentration of all the chemicals present? Most probably these guys will be 0, only A will be there. If A is also 0, nothing is happening in your reactor. Okay, so A has to be there, and then because of reaction B, C, D will get produced. Okay, so but you could have a, for the sake of generality, I am writing these, could be 0, could be non-zero. Now we call this the initial condition because most of the time when we are talking about dynamics simulations, your independent variable will be time, okay, and you know what the conditions are at time t equal to 0, and you are trying to understand what is going to happen at later time instance. So initial condition means at time t equal to 0, but that can be, so but as far as mathematics is concerned, it just a variable, t is just a variable. You could have also problems where, which are of the nature of initial value problems, where the independent variable is not time. Okay, I will give you an example. So basically what I am saying here is, this problem of this batch reactor is an initial value problem, or I call this IVP, and here basically IVP means all the variables are specified at the same time instant. Okay. So let us take another example from let us say heat transfer, simple heat exchanger problem. Okay. So shell and tube, I think there is a better, more specific name, heat exchanger. Okay. So these are basically two concentric tubes, they do not look concentric, but they are concentric. Okay. So just and there is one, this is your core and this is your annulus. What we have is a situation where let us talk about co-current flow. So both the hot fluid and the cold fluid are both coming from the same, flowing in the same direction. So let this be this z axis, because we are talking about, you know, a cylindrical coordinate system, you want to look at r theta z as your independent variables, that is z. Okay. And I am going to put this hot fluid inside, which has a temperature given by Th, a cold fluid outside which has a temperature Tc. That is the variable. Tc is the temperature of the cold fluid which is flowing in the annular region. The hot liquid is coming here, and this is Z equal to 0 inlet. What we expect to see is that the hot fluid is going to lose heat and its temperature will decrease. Okay. The cold fluid will gain heat and its temperature will increase as it flows in the Z direction. So, basically what we are looking at is how does the temperature change with the flow? How does TH and TC change with flow? Okay. In the Z direction. Now, there could be variations in the R direction also, okay, in the theta direction. Right now, for the sake of simplicity, to make my point, I am neglecting all of that. Okay, when we talk about partial differential equations, you will see that. So, TH, TZ, or TC are functions of Z. Okay, and I am going to assume steady state. Steady state means things that don't change with respect to time. Okay. Variables do not change with time. That is the assumption. Now, so in this case, we want to do a conservation of energy. Okay, earlier we did conservation of mass and momentum. So now since we are talking about temperature, heat energy, okay, we want to do conservation of energy, and if you want to do this, if you want to do a shell balance, so we apply conservation of energy. Remember, this is what I said, this is the modeling part where I apply the conservation law to get my equation, and there are two variables here, Q, H, see. So, let us, what is rho? The density. So, this is the density of either the cold fluid or the hot fluid. Okay. The subscript H is for hot, C is for cold, because two different liquids, and this is density. This is your specific heat, and this is your flow rate. Okay. U is my overall heat transfer coefficient. So, because then overall I am not worried about the thermal conductivity and the resistance of the pipe and all that. There is an overall heat transfer coefficient. The driving force is Th minus Tc. Okay, everything is combined into U. P is the perimeter. Or 2 pi r, over which the heat transfer. So, basically I am looking at the heat transfer from the surface, the radius of the inner core. Now, you may wonder what happened to this outside guy, because the cold fluid is also going to either lose or gain heat from the outside, ambient atmosphere. So, I am going to avoid that, and I am just going to just say that this is insulated. Okay. If it is not insulated, I will have one more term here for the cold fluid. The hot fluid is only exposed to the cold fluid, but the cold fluid is exposed to both this and the ambient. So, I am preventing any heat transfer, heat loss to the ambient by insulating. But that is what you would do, right? You do not want to lose heat to the ambient unnecessarily. So, insulate, right. So, that is basically, otherwise I will get one more term. So, here again, I mean, we have made some assumptions. We are neglecting, for example, variations in the radial direction, okay. We are assuming temperatures only of Z. We are assuming this overall heat transfer coefficient takes care of the whole thing. The point is, this also is a system of linear equations, okay, because my independent variables are Th and Tc. Sorry, my dependent variables are Th and Tc, and they are all occurring to the power 1, and the derivative is also occurring to the power 1. I will also call this an initial value problem, because at Z equal to 0, I am specifying the temperature at the inlet. So, since my system is a co-current heat exchanger, so at Z equal to 0, Th equals Th in and Tc is equal to Tc in. This is the inlet temperature, okay. Again here, all the variables are being specified at the same point at Z equal to 0, okay. So, this is again an example of an initial value problem, although now my independent variable is not time, it is Z. How does how do people, there is no difference. Physically we say Z is this space and T is time, but as far as mathematics is concerned, I am only looking at are all the variables specified at the same point, okay. So, this is also an initial value problem, since both Th and Tc are specified at Z equal to 0, okay. So, although initial means normally you think in terms of time, so it has nothing to do with time, it has to do with the fact that are all the things specified at the same point. Supposing this had been a counter current flow, then you will specify at Z equal to 0 one temperature and at Z equal to L another temperature. So, that is not an initial value problem, because the two variables are being specified at two different points, okay. We would call that a boundary value problem. So, if the heat exchanger was counter current, then we specify one variable at each end, okay, one is specified at the left end, one at the right end. So, for example, say Th is equal to Th in at Z equal to 0 and Tc is equal to Tc in at Z equals L. Now, I will call this up, this is not an initial value problem, because the two variables are specified at two different points, okay, and this is okay. So, again what I want to do is I want to rewrite this in the form of a matrix operator like we did earlier for the other two problems. So, what we are doing is we are writing all the governing equations and then we are writing it in the form of some matrix, okay. So, I want to do the same thing here. So, my unknowns are, so I am going to divide this equation by rho h Cph, this term here, so that I have a coefficient 1 for the time derivative, okay. So, if I divide by this first equation by this coefficient, second equation by this coefficient, my coefficient of the time derivative of the first order derivative will be 1, okay. So, that is what I want to do. So, I have d by dz of TH was my first equation, TC is my second equation, equals, again I write it as TH, TC, okay, and what will be the things multiplying this here, minus UP divided by QH, let me write it in the same order, rho H, CPH, QH, minus that plus UP divided by rho H, CPH, QH, and in the second term I will get plus UP rho C, CPC, QC, H, QC. Yeah. So all I did is divide by that, and TH is with the positive sign, and this is with the minus sign, minus and that's plus. Yeah. So now this is my matrix A. Oh, A times U. A is this matrix now. Okay. So we are going to talk mainly about initial value problems. So basically we are looking at the situation where the variables are all specified at z equal to 0. So here at z equal to 0, u equals u naught. So I am going to just stick to this, try and stick to this notation of u being the vector which contains all my unknowns. Okay. Again, for a particular problem, you know all these values, you can substitute it inside and you can solve. And that is the advantage of doing the modeling part. You want to change your flow rate, you just have to change the Q and solve, you get the behavior of the system. Okay, you want to change the liquid, you change the density, change the specific heat and run do the calculation. So, okay. So that's again I showed you a subtle difference between the initial value problem and the boundary value problem. Okay, boundary value problem means conditions are specified at two different points on the boundary. Initial value problem means all conditions are at one point. It could be time, it could be space. We have done fluid mechanics, reaction, heat transfer. So I think there's one thing, maybe mass transfer, reaction. Okay, let's look at a partial differential equation. So first we saw algebraic, then we saw ordinary differential equation, now we are looking at partial differential equation. So I mean there could be different problems you can look at, say diffusion in a catalyst, okay, maybe reaction and diffusion. Or heat transfer in a spherical particle. And that's basically, I mean, you must have done this problem. So let's look at the second problem first, where if you write this equation, you'll get this. So what we have is a spherical particle, okay, which is, let us say, at a high temperature, and I am suddenly dipping it in a cold liquid. Okay. So, I have a spherical particle, and this is at some temperature T naught, and this is ambient. Thank you. Yeah. So, yeah, this is your otherwise what first of yeah, this is the accumulation term which has the time derivative in it, and if this is also R, it's not a partial differential equation, it's only a function of R. So, basically temperature is a function of R and T, that is what we are trying to show. Okay, good, thank you. So, now what is going to happen is, because of the finite thermal conductivity of the catalyst, the temperature is going to be a function both of R and T, that is the physical problem. Okay. So, temperature is a function of R and T, and what we want to do is, we want to find out what is the dependency on R and T. To find out what is the dependency on R and T, you have to solve this equation. Okay. Again, for the particle density specific heat, this is the thermal conductivity, and that is your Laplacian, because I am assuming heat transfer only by conduction, there is no convection or anything. So, only conduction and change with respect to time. Okay. So, this has to be solved subject to some boundary conditions. So, physical problem is a particle at a high temperature being placed in a cold liquid, is losing heat. It could be opposite, cold particle in hot, no problem. Okay. And we are interested in finding out how does the temperature change. For that, you write the energy equation, and you have to solve the subject to some boundary conditions and initial conditions. At T equal to 0, this is the initial condition, temperature is equal to, let us say, T naught, and the boundary condition will be at R equal to 0, temperature is bounded, and at R equals R, let us say the temperature is equal to T ambient. I mean, I am just writing representative boundary conditions. We will possibly look at some details later. Basically, I am saying that the heat transfer coefficient is so high that we have temperature is equal to T ambient. There is no temperature gradient in the ambient liquid. Okay. This boundary condition implies no heat transfer resistance in the ambient. Okay, there is no, therefore, on the surface it is T ambient, it is not, there is no gradient. Anyway, to cut a long story short, this is again a linear equation. This time derivative is to the power 1, this is a second order derivative, so all the derivatives also will be to the power 1, there is no power to the derivative. The boundary conditions are all specified. Okay. So, basically this is an example of a partial differential equation which arises in your heat transfer. Similarly, we can look at problem in maybe mass transfer. Only thing is, instead of temperature, I can put concentration. Okay. So, now dC by dt, now I got it right, ds by r squared, or no, d by r squared So, here a slightly different problem in the sense I have a spherical particle and there is a chemical reaction going on which I am assuming to be first order. Okay. So, this is your reaction term. So, this is an example of a spherical catalyst sustaining a first order reaction. Okay. So, again in my catalyst reaction is happening, so concentration is going to change with time as well as with R, okay, and there is a reaction also which has to be included because it's occurring inside the catalyst. So, I mean I am not bothered to derive these equations, you are supposed to know these, or at least you do not have a choice, you have to accept this now, okay. So, now this is again an example of a linear system, okay. Again, because I am assuming first order, if it is not first order, then it may be non-linear. So, what I have tried to show is that there are different systems in the chemical engineering, could be mass transfer, momentum transfer, heat transfer, reaction engineering, where you come across a whole bunch of problems, okay, and we have restricted ourselves only to linear equations, and as long as your equations are linear, you can always rewrite this in the form of some matrix operator, okay, that is what we saw. And the point is, you have looked at solving these different classes of problems using different methods. For example, if you have a system of linear algebraic equation AU equals B, I mean you were looking at Kramer's rule or something like that, Kramer's rule, right? Yeah, some method for solving those equations, or you did manipulation algebraically, you try to eliminate some variable from 3 equations, eliminated 1, got 2 equations, eliminated 1 more, and then you did that. So, you ended up solving the problem. And ODEs, I mean sometimes you were doing separation of variables, and numerically you did Runge-Kutta, okay. Partial differential equations, again you did separation of variables. So, the point is, what I want to do is, I want to tell you that we can have one methodology which can solve these different classes of problems, okay, and that is what we are trying to do. So, these 2 lectures we just looked at different situations where different kinds of problems arise, okay, but although one is a partial differential equation, one is an ODE in Z, one is an ODE in time, one is a algebraic equation, we are going to establish the framework by which same idea can be used for solving all of this. So, it is not that you are thinking about having to remember different techniques for solving different problems. So, if you understand the philosophy, then you should be in a position to use a same approach for everything, okay, and hopefully you develop this perspective. So, tomorrow in some other situation, some other context, you will also think in terms of having one unified framework, one general framework for solving problems. That is what we are trying to get at, okay. I am illustrating it with maths. In some other context, you will see that similarity between dissimilar things. So, the whole idea is, things may appear dissimilar, but they are actually similar, and if you can develop the ability to understand this and comprehend the similarity between dissimilar things, then you have learned a lot, okay. Okay, let us stop now. What we will do in the next classes, we will start looking at some abstract concepts, because we have to get some abstraction, so which will help us develop this framework. So, we will talk about vectors, vector spaces, which will help us analyze all these different systems in the same framework, okay. Thank you.